Hi, in this lesson we are finally going to learn to actually add, subtract, multiply, and divide with vectors. Let's start by looking at our first example of the two soccer players. As you recall, the player without the ball first ran 3 yards to the right, and then 4 yards down. And we wanted to know how far away she was after her run, or in other words, how long the pass to the new position was. Essentially what we were doing here was adding displacement vectors. Another way to phrase this problem is asking if we add a displacement of 3 yards right to a displacement vector of 4 yards down, what will be the result? We know it won't be 7 yards. We can see in the picture the two players are not 7 yards apart. They are much closer than 7 yards, so we can't add, subtract, multiply, divide vectors like we could just normal scalar numbers. In fact, in this situation, we have a right triangle and can use Pythagorean theorem with the two vectors to determine the magnitude of the final displacement, which was 5 yards. The take-home point is that vectors are different than scalars, and we have to use different techniques to add, subtract, multiply, or divide them. So let's start with adding vectors. Adding vectors is super easy using the arrows. We can use a technique called tip to tail. Let's take vector A and add it with vector B. To do this, we draw one of the vectors. We'll start with A, and then draw the next connecting its tail to the tip of A, like this. So tip of A connects with tail of B. Then the final vector, what we call the resultant vector, is drawn from the starting point of A to the final vector's tip. And that's it. This can be done with any sort of vector. Let's take a look at another example. Vector A plus vector B, draw the first one, draw the second one, connecting the tip of the first to the tail of the second, then draw resultant from beginning to end. Same thing. Make sure the resultant is drawn from the first tail to the final tip. It does not follow the same pattern as the pieces. If all of the pieces point down, then when you add them together, the resultant should also point down. Mathematically, we may write this as vector A plus vector B equals vector C. But remember, we cannot just add the magnitudes of A and B to determine the magnitude of C. When you see a little vector arrow symbol over the variables, that's when you know you are dealing with vectors, and you need to be careful. Let's look at one more example that will provide insight into how we solve this mathematically and with our programs. Again, two vectors, A plus B. Add them tip to tail and draw the resultant vector. Now here's the fun part. Let's draw the x and y components of all three vectors. First, the x and y components of A should be familiar to you by now. Second, the x and y components of B. And finally, the x and y components of C. There's a lot on this one diagram, so let's isolate the x components of all three. What we can see is that CX, the x component of the resultant, is actually the same length as AX plus BX. So we can say AX plus BX equals CX. And we can do the same thing with the y components. The full diagram again. And now, just the y components. Again, we can see that the components AY plus BY equals CY. Pulling all of this together. To mathematically add vectors A and B, first break the two vectors into components. Use trig to break into the components. Add the x and y components. Then combine the results with Pythagorean theorem. Before we see how to do this in Python, we have to be careful with our directions of vectors when we have more than one of them. For example, if I have one vector pointing 10 degrees north of west, and one vector pointing 10 degrees north of east, you'll notice that their y components are pointing in the same direction, but their x components are pointing in opposite directions. When I add them together with tip to tail, the opposite x components have added to 0 or canceled each other out, and the resultant vector is pointing straight up. That's because when we deal with opposite directions, left, right, or up, down, or east, west, etc., one direction must be positive and the other direction negative. Makes sense conceptually, and this is consistent with your normal xy axis. To the right is positive x, and to the left is negative x. Same with the vertical axis. In order to make it easy for us to be consistent with which direction is positive or negative, we set up the angles so that when we use them, they will automatically determine the positive and negative directions. It's pretty simple. You measure all of the angles from the positive x-axis. Above it, you have a scale of 0 to positive 180. Below it, you have a scale of 0 to negative 180. With this scale, the trig calculations will automatically determine the positive and negative directions. For example, let's take the x component. We want every x component pointing to the right to be positive, and every x component to the left to be negative. If we look at the math to calculate the x component we've been using, hypotenuse times cosine angle, with angles smaller than positive or negative 90 degrees, like 30 and negative 30, the calculations give us positive values. When the angles are greater than positive or negative 90 degrees, like 120 and negative 120, we get negative values. Exactly what we'd expect and hope. The same will be true for the y components too. All you have to do is be careful to set up the angles with this scale, and the math will do the rest. Awesome! Now it's your turn to try this in your programs.